Hi, everyone. Welcome back. We're going to start on chapter 7. In chapter 7, we're going to discuss 3 physical states: gases, liquids, and solids. In this chapter, we will first briefly talk about more detail about these 3 physical states and why, what they are, and also what determines or what affects the 3 physical states. And then we're going to spend a larger part of the chapter talking about gases, because a lot of or some gas properties or variables are related mathematically. And then the last part of the chapter, we can talk about the change of states, the changes between liquid, solid, and gas, and what causes the change. And then so we're going to focus a little more on evaporation, that is the change from liquid to gas state. So that's basically the structure of this chapter. And then let's get started. Okay, first, in order to understand physical states, these 3 physical states, okay, we first need to throw you out. The reason I call it throw you out, because this is a very complex theory, but here we just put it here, these 5 facts called kinetic molecular theory of matter. You need to understand these basic facts about matter and also the particles that made up this matter to fully understand why something adopts a certain state and why temperature or pressure, for example, affects these different states. Okay, again, the reason I said in this fundamental class, we call it throw out the theory, because it's actually more complex study about these topics, but we summarized a very complex theory called the kinetic molecular theory into these 5 facts. Okay, I'm going to go over these facts. It should be easy to understand. And after you understand, you have a better understanding later on about physical states, about these 3 states. And we're going to use these facts, and we're going to talk about these facts, one or more items throughout this chapter when we explain the behavior of 3 physical states. Okay, let's take a look. The first one is matter is composed of tiny particles. Okay, tiny particles. These particles could be atoms, could be molecules, or could be ions. Okay, they're constructed by these particles. And these particles have definite size and characters that do not change. But the bottom line is matter is composed of small particles. Number 2, the particles are always in motion, constant motion, random motion. And because of that, they possess kinetic energy. That is the energy of motion. Now, something is moving with the mass that is moving, like your car, like your ball, football, basketball. As long as the particles are in motion, they possess kinetic energy. Okay, they possess kinetic energy. And number 3, because they are in motion, their property, especially their velocity, will increase as the temperature increases. Because as the temperature increases, better understanding is the particles are going to move faster. Okay, they have more energy to move faster. So the velocity is going to increase, and the kinetic energy also increases. So in summary, that is, the kinetic energy is related to temperature, because higher temperature, velocity is higher, kinetic energy is higher. Particles move faster. Number 4, the particles interact with each other. They interact with each other through either attraction or repulsion. Okay, either they repulse each other or attract, but they're interaction with each other. And because of the interactions, the electrostatic interactions, either repulsion or attraction, the particles possess another type of energy called the potential energy. Through that interactions, okay, they're interacting with each other and called potential energy. And finally, the particles in the system can transfer energy from one to another or to each other through collisions. Okay, through collisions. And we put a word elastic collision here. Okay, this word means during the collision, there's no energy loss. We assume that's ideal situation. Okay, there's no energy loss during that collision. So 5 facts about matter. We call that kinetic theory. Okay, it is a summarized version, but it's very useful, and we're going to use these to explain many things in this chapter. Okay, let's go over these 5 facts again. The first, matter is composed of small particles. Number 2, the particles are always in motion, constant motion, so they possess kinetic energy. Number 3, kinetic energy increases as temperature increases because the velocity increases of the particles. Number 4, the particles interact with each other through electrostatic forces. And because of that interaction, either attraction or repulsion, these particles possess kinetic energy. Potential energy. And number 5, the particles can transfer energy from one to another through elastic collision. The particles can collide with each other. So these are the 5 facts, okay, about matter. Again, you will see how we use them in our lecture today, okay, in our lecture of this chapter. Now, remember we said the particles possess 2 types of energy. One is kinetic, one is potential. And these 2 types of energy are actually opposite to each other. Because kinetic energy tend to what? Tend to move things apart because particles are moving around in motion. So kinetic energy is kind of like disruptive force, okay, like a break things apart, okay, making the particles breaking apart. And kinetic energy, like we mentioned, is related to temperature. Higher temperature, higher kinetic energy. Okay, that's one thing. But potential energy, because it's from interaction of these particles, mostly attraction interactions. And this energy is now responsible for holding particles together because remember interaction, attractive interaction. So kinetic energy is breaking them apart, but potential energy is kind of holding them together. And we call that force cohesive force. So one is disruptive, one is cohesive. They're kind of opposite to each other. But again, 2 of these opposite forces, only one, that is the kinetic energy, is depending on temperature. So that means temperature plays a major factor to determine the physical state of a given matter. Higher temperature means what? Higher disruptive force, because higher temperature is higher kinetic energy. So your particle will more likely to be what? To be disruptive. What state is disruptive? Liquid and gas. Okay, they're more disrupted. The particles are separated. We have seen that picture in chapter 1. But if temperature is low, kinetic energy is low, then the cohesive force may dominate. If that's the case, particles are held together stronger. So you more look likely will expect solid and liquid. The liquid is something between. So temperature becomes very important, determining whether a sample adopts what state, because temperature changes kinetic, the disruptive force. Okay, here is what we know about these 3 matters. Okay, the top part we have actually seen before in our previous chapters. Okay, for example, solid has definite volume, definite shape. Liquid has definite volume, but indefinite shape because it adopts the shape of the container. Okay, also, the particles for solid, they are very fixed arrangement and close to each other. Liquid, something between. Gas, the arrangement is random, it's separated. And about the forces, okay, solid, the forces are very strong. I mean, cohesive is very strong. Gas, cohesive is basically zero. You only got kinetic because the particles are separated. So they don't even have interactions, attractions. So cohesive is very weak, almost zero. It's disruptive. And liquid, again, something between. And finally, which energy dominates? For solid, apparently because they're holding together, cohesive or potential energy dominate. Kinetic is less than potential. But on the other hand, gas, like I said, there's no cohesive force. So there's barely any potential energy. The particles all have kinetic. So in gas, kinetic energy, the disruptive force dominates. And again, liquid is something between. Disruptive and cohesive are the same range. That's why it's something between. So you see that these are the three different states. Their properties are different because their particles are different, including the particles are arranged differently, and also the particles energy-wise, they're different. Okay, solid held together, cohesive force dominates. Gas separate, kinetic energy, disruptive force dominate. Liquid is always something between. Okay, you can take a look at the chart in detail after, or you pause the video. Now, this is the first, like we said, we briefly give an overview of these three states. We know what they are and why they are and what affects them. Okay, what causes them to be different states? Because the particles. Okay, we explained using the particles. And then we're gonna use these 5 items again. So always keep that in mind. But next, we're gonna jump to one of the physical state, the gas state. Because like I mentioned, in gas state, the variables of gases or some property of the gases are related mathematically. And that relation, mathematical relations, we call gas laws. Okay, gas laws. So in this part of the chapter, we basically want to study these gas laws of gases and how their properties are mathematically related together. Okay, first, what properties, what variables we're talking about? Okay, the variables we're talking about here in gas laws are the amount of gas, that is in moles, like we said, amount, basic unit is mole. The volume, the temperature, and the pressure. Okay, these are the 4 variables that a gas will have. The amount, the temperature, the volume, the pressure. I think 3 of them you can understand very easily. The mole, how many mole is this? What's the volume of the container, and also temperature. These are easy to understand, but we need a few more words talking about pressure. What is pressure? Okay, pressure by definition in physics is the forces applied per unit area. So force per area. That's called a pressure. Okay, forces per area. So in order to have a pressure, you first need what? Force. So what is the force for gas? What is the force that causing gas pressure? The force that creates gas pressure is exerted by gas molecules constantly collide with the wall of the container. So here comes these kinetic theory again. Remember, particles of gas, they are made by particles. They are always in constant motion. If they're in constant motion, it means what? They have velocity, they have kinetic energy. So there's a chance these particles keep colliding the wall of the inside wall of the container. And that collision will exert forces on the wall, and force per area is the pressure. So the pressure of the gas comes from what? The gas molecules or gas particles collide the wall. To collide the wall. When we talk about pressure, okay, there's one pressure I want to mention, or I want you to know about, is the pressure of our atmosphere. Okay, the air we breathe, there has a pressure as well. It's gas, right? So how do we measure it? Okay, how do we measure it? And now we know, even you can check your iPhone app, you will see that the pressure of our atmosphere is approximately 760 millimeter mercury. What does that mean? Okay, you can see your app. What does it mean? It came from this experiment that measures, okay, that measures the atmosphere pressure. Okay, you use a long tube, fill the tube with mercury. The tube, of course, is one end open, one end closed. You fill the tube with mercury, then invert it and insert the open end into a bowl of mercury. Okay, and that's the basics of a barometer. That's basically how the pressure of the atmosphere is measured. Now, once you insert the open end into the bowl of mercury, you release your finger, the mercury is going to drop, but not all the way down. At a certain point, you will see that the mercury remains that height, meaning the atmosphere pressure is supporting that mercury pressure, the height of the mercury. And of course, at sea level, the pressure of the atmosphere can support a height of 760 millimeter mercury. Okay, why they can support? I put it here. The force of the air on the surface of Mercury balanced by the gravity pull of the column of Mercury. Okay, of the column of Mercury. So they're balanced out. Okay, water surface pressure exerted on the surface of the bowl balanced with the height of the mercury pressure. But again, at sea level, the atmospheric pressure can balance 760 millimeter mercury in height. And that 760 millimeter mercury is used as a unit of pressure. Okay, unit of pressure. That's called 1 atmosphere pressure. Okay, 1 atm. What is 1 atm? Is 760 millimeter mercury. And now around us, our gas pressure, our air pressure is not exactly 760 because sometimes weather change or we're not exactly at sea level, but usually we assume the atmospheric pressure is 760 or very close to 760 mercury. And also there's another unit of pressure, which is torr. Okay, 1 torr is 1 millimeter mercury. So 760 millimeter mercury is 760 torr. It's an old unit for pressure. And these are 3 units. You will see them in this chapter. And you know, we have studied before, if you were given 1 unit instead of another, how do we convert? Okay, how do we convert? And finally, 1 atmospheric pressure is about 14.7 psi, which is probably the gas pressure unit you're familiar with, because that's English unit. Okay, psi stands for pounds per square inch. Okay, pounds per square inch. Okay, very concept check. Do you still remember the 4 variables for gas loss? Amount, temperature, volume, and pressure. So answer is A. Keep in mind, none of the others are. Only these 4 are the variables for gas. Okay, now, after that, let's take a look how these variables are related to each other mathematically. The first gas law, is called the Boyle's law. In this gas law, 2 variables are related if the other 2 are fixed. If temperature and the amount of the gas are fixed, that means they're constant, then the pressure of volume multiply, the product of pressure times volume will be a constant. In another word, because pressure and volume multiply together is a constant, means what? Means pressure increase, volume gonna decrease, or pressure decrease, volume gonna increase, because the multiply here is a constant. You cannot both increase or both decrease. So pressure and volume will be inversely proportional. Okay, inversely proportional. What does it mean? It means one increase, one decrease, one decrease, one increase. Mathematically, Boyle's law can be represented using this equation. P1 times V1 equals to P2 times V2. 1 and 2 stands for what? Two states, before and after. Remember we said P times V is a constant. So before P times V, we equal to after P times V. That's why 1 and 2 means. Okay, 1 and 2 means before and after. And you can see that this is a very simple experiment plus numbers to show you Boyle's law. Okay, pressure times volume, 800. Pressure times volume, 800. Pressure times volume, 800. You see that? Means what? Higher pressure, the volume will be smaller. Lower pressure, volume will be bigger. If you press down the piston, the volume would be smaller, and the pressure will be higher. But pressure multiplied by volume should be a constant. Okay, no matter what the volume and pressures are, but they multiply together, there must be a constant. And that is called Boyle's law. And again, the mathematical equation is this one. Okay, this one. So here's a quick exercise. Okay, quick exercise. It says a sample of helium gas occupies 12.4 liter at 23 degrees and 0.956 atm. Then the question asks you, what is the volume will be if the pressure is 1.2 atm, assuming that the temperature stays constant. So temperature is the constant, and the helium sample is constant, and we don't say we're not adding helium or not. So this is the perfect example of Boyle's law. Okay, Boyle's law. And we know that Boyle's law, okay, Boyle's law, what we need to do is, let me copy that down here. Okay, what we need to do is find out P1 and P2, V1 and V2. Okay, because Boyle's law, the mathematical equation is P1 times V1 equals to P2 times V2. Right, that's the mathematical equation. So all we need is to ask what is P1 and V1 is P2 and V2. We know the first pressure is 0.956 atm. So that's the P1. And at that pressure, the volume is what? 12.4 liter. So P1 times V1, we got it. Then after that, it asks at 1.2 atm, that is P2. Then what is the volume? V2, we don't know, because that's what we need to solve. So now you know P1 times V1 equals to P2 times V2. But you need to read the question carefully. You need to figure out which one is 1 and 2, and the other, which one is 2. When pressure is 956.956, the volume is what? 12.4. So these two are together. These two are either 1 or 2. It doesn't matter, in fact. But you need to know these are the one that are the same state. Okay, same before, either before, after. These two are multiplied together. So after that, all you need is divide P2 on both sides. Okay, divide P2 on both sides. You get the equation V2. Okay, V2 equals to P1 times V1 divided by P2. Okay, because you divide P2 on both sides, you got V2. Okay, V2 equals to P1 times V1 divided by P2. Okay, you put the numbers in. 0.5956 times 12.4 divided by 1.2. You get V2, which is 9.88 liter. Okay, 3 sig fix, you keep 3 sig fix. And the unit is volume. the volume of the unit is liter, because ATM cancel with ATM, you keep the original unit. In Boyle's law, you don't need to change the unit. Just make sure the units are consistent. If the pressure unit is ATM before, you better to use the ATM the same after. Then your volume units are also consistent. Okay, that's the first gas law and also a practice. The second gas law called Chaucer's law. Okay, called Chaucer's law. In this gas law, we have to fix the volume. We have to fix the pressure and amount. So that means if we have a Chaucer's law applied, the pressure of the gas must be constant. And of course, the amount of the gas must be constant. That means the container has to be sealed. If that's the case, volume and temperature is proportional, directly proportional. Means what? Volume higher, temperature must be higher. Or higher temperature, higher volume. Mathematically, if they're proportional, you have this equation. V over T equals to V over T. V1 over T1 equals to V2 over T2. Higher pressure, higher temperature, higher volume. Lower temperature over volume. The ratio will be the same. You can see that experiment. Volume over temperature, volume over temperature, volume over temperature equal the same number. 0.2, 0.02, 0.02 if you do the math over there. Now, in order to use Chaucer's law to do the calculation, one thing is very, very, very important. That is the temperature unit. In Chaucer's law, the T, you can see that I'm using even capital T. The temperature has to be Kelvin. Okay, if you remember, we studied 3 temperature scales in chapter 2. If you forgot, you can pause the video and go to chapter 2 video. Take a look at the 3 temperature scales. In gas laws, including the Chaucer's law here, the temperature unit must be Kelvin in all gas laws, no exception. What is Kelvin? Kelvin equal to Celsius plus 2673. If you were given Celsius, you need to add 273 to convert it to Kelvin. Okay. If you were given in Kelvin, you don't have to worry about it. You won't be given Fahrenheit. Like I said, normally in scientific literature and textbooks, Celsius and Kelvin are the units we use. But if you were given Celsius, make sure you add 273 to convert Celsius to Kelvin. And all gas laws, the temperature must be Kelvin. Otherwise, your calculation will be wrong. Right? So let's take a look. Suppose a balloon containing 1.3 liter of air at 24.7 Celsius. Okay, you can see that we have a volume, we have a temperature here. It's placed into a beaker containing liquid nitrogen, and the liquid nitrogen temperature drops to minus 78.5 degrees Celsius. You have another temperature. They ask you, what is the volume of the balloon now, of the air now? Of course, if it is a balloon, it is in the atmosphere. So the pressure always equal to the atmosphere. Otherwise, the balloon will either collapse or explode. So the pressure is constant. And the balloon is sealed. You're not poking the balloon open. So the amount of gas inside the balloon is also constant. So this is a perfect example of Chaucer's law. Okay, Chaucer's law. What is Chaucer's law? V1 over T1 equals to V2 over T2. The only thing we need to ask, what is V1 T1? What is V2 T2? So V1 we know is 1.3 liter. T1 is 24.7 Celsius. Like I said, if you were given Celsius, you need to add 273 to convert it to Kelvin. So T1 is 297.7 Kelvin. After that, we don't know volume. We don't know V2 because they're asking V2, but we know T2, which is what? Minus 78.5 Celsius. Again, add 273 to convert it to Kelvin, which is 194.5 Kelvin. So we got V1, T1, and T2. We only need to solve what? V2. Okay, solve V2. Okay, let's write it down. V1 over T1 equals to V2 over T2. Okay, over T2. We're asking V2. So here, what I can do is multiply T2 on both sides. So I got V2 equals to V1. Oops. Erase them all. Eraser here. Sorry. It's hard to write with a mouse. Again, I'm multiplying T2 on both sides. So I got V2, okay, V2 equals V1 times T2, because I multiply T2 on both sides, and then divide by T1. Okay, that's what I got. Rearrange that. Okay, multiply T2 on both sides. So V2 equals to V1 over T1 times T2. So I plug in the numbers. V1, 1.3 liter. Keep the unit when you do the calculation. T2 is 194.5 Kelvin divided by T1, 297.7 Kelvin. Oops. Okay, let me see if I have something calculation here. Just copy here instead of showing drawing on the mouse. Yes, I have it. We have it. So down here. Right. So V2 equals to V1 divided by T1 times T2, because I do it on both sides. And then what I got is V1 is 1.3 liter times T2, which is 194.5 Kelvin, divided by T1. Okay, divided by T1, which is 297.7 Kelvin. Okay, that's it. So after that, you can see that V1 again, okay, V1 again is 1.3, V2 is times T2, which is 194.5 divided by T1, which is 297.7 K. So after that, you get the volume of V2, 0.849 liter. You can see Kelvin and Kelvin is actually canceled. Okay, you got liter and 3 sig figs. I'm keeping 3 sig figs of 0.849 liters. All right, so that is the calculation for Chaucer's law. Okay, Chaucer's law. A very quick question asking you to decide this scenario whether it applies for Boyle's law or Chaucer's law. I think it's very straightforward, but let's take a look. To hide a helium-filled balloon for a birthday party, you decide to place them in a chest freezer. When you retrieve them, you were disappointed to find the balloons deflated, right? You put in the freezer. As they warm up, they actually return to the original size. So they ask you what gas law is demonstrated in this scenario and what happened to the kinetic energy during the warming process. Okay, first, we know we have a balloon. When it's cold, the volume shrinks, right? Balloon deflated. When it warm up, you take it out, warm up, the balloon go back, and we warm volume increases. So we know it's actually the changing of volume by what? By temperature. Higher temperature, bigger volume, lower temperature in the freezer, small volume. So we know this is Chaucer's law. Okay, Chaucer's law. And they ask you what happened to the kinetic energy during warming. We know warming process means what? Temperature increases. If temperature increases, we know kinetic energy always what? Increases. So answer is D. This scenario applies Chaucer's law, and the kinetic energy increases as the temperature increases during the warming process. And here's the picture of the experiment. Okay, very similar, of course, not the same. Okay, you put the balloon in ice water, the balloon will shrink because temperature is lower. Lower means lower kinetic energy. If you point the balloon in boiling water, the balloon will expand because higher temperature, higher volume, bigger volume. The pressure of the balloon is the same because they're in the atmosphere. Okay, that's Chaucer's law. You can actually do this at home experiment. All right. Now, after we talk about two laws, the Boyle's law and the Chaucer's law, you will find out one is relating pressure and volume, another one is relating volume and temperature. And if we combine these two together, okay, still pressure multiplied by the volume divided by the temperature, right? Pressure multiply volume and divide by temperature, you will find out we can create a new law called combined gas law. Okay, combined gas law. This law relates not only two variables, but three variables. But this law, the reason it's combined because it contains both of the previous laws we studied. P and V are still inversely proportional because they multiply each other. V and T are still proportional because they divide each other. So applying the mathematical relation of these two laws, we got a new, better law, combined gas law, because it relates three variables, P, V, and T. Okay, P, V, and T. Now, P, V, and T, combined gas law, meaning we now have six variables, like before and after, we have six of these amounts, P1, V1, T1, P2, V2, T2. So if you want to solve one, you have to know the other five. You have to do some mathematical rearrangement. Okay, because there are six, P1, V1, T1, P2, V2, T2. And at this point, I gave you a web assignment, I think. And in the web assignment, there's a video actually showing you the exact, how do you solve any one, knowing the other five. And most importantly, how do you rearrange that combined gas law into whichever format you want? Okay, so please, if you don't know how to rearrange the mathematical equation like this one, pause the video, go to the web assignment. It's going to be very helpful because it gives you stepwise math rearrangement to show you how do we get one if we know the other five, and how do we rearrange this gas law. Okay, again, pause the video if you need help, but if not, here's the exercise. The exercise tells what temperature does 121 milliliter of CO2 at 27 degrees Celsius and 1.0 ATM. So you see that in this three, you know that these three P, V, and T are actually at the same place. They're the same stage. Okay, 1.21 milliliter of CO2 at 27 degrees Celsius and 105 ATM. So that's one set of data. Then this gas occupy a volume of 293 mil at a pressure of 1.4 atm. So 293 mil and 1.4 is another set of data. And then, of course, there is only pressure and volume. That means that's why they're asking temperature. So with that, you can list P1, V1, T1, and P2, V2, T2. Okay, P1, 1.5. P2, 121 mil. And T1, okay, sorry, P1, 1.05 atm. V1, 121 mil. T1, 27 degrees Celsius at 273 converted to Kelvin. Keep that in mind. All gas laws, temperature has to be Kelvin. That's one set of data, 1, 1, and 1. Then another set of data, we know P2 is 1.4 atm. V2 is 293, those are given. They ask T2. See, 6 of them. In order to know one, you have to know the other 5. The only thing you need to do is rearrange. Okay, rearrange the gas law, the combined gas law. P1, V1 over T1 equals to P2, V2 over T2. Need to know T2. Okay, one method, the one I'm using, okay, is you do a cross multiplication. Okay, meaning P1, V1 times T2, because P1 we across is T2, equals to P2, V2, and T1. You multiply cross. P1, V1 times T2 equals to P2, V2 times T1. So I convert the ratio into 2 multiplication. Now we know we want T2. So I divide P1, V1 on both sides. I need T2. So I divide P1, V1 on both sides. I got T2 equals to this divided by P1, V1, because I divide P1, V1 on both sides. So that's the rearrangement. Now I know how to solve T2. I just need to do this. P2, V2 times T1 divided by P1, V1 in a parenthesis. All you need now is what? Plug in the numbers. What is P2? What is V2? What is T2? And then what is P1? What is V1? They're all known because we listed them in the first beginning place. And then all you need is solve it. Okay, of course, in this question, okay, in this particular question, well, after you solve, the temperature is in Kelvin. They ask you Celsius, so you have to convert it back to Celsius by do a subtraction of 273. Okay, again, the answer here, T2, will be in Kelvin because it's from gas law calculation. The question, this question, unique question, specifically asks for Celsius. You need a minus 273 from Kelvin to get Celsius. Finally, we know the previous combined gas law relates 3 variables. The other variable, which is the amount of the gas, is not included. That means all the previous gas laws, you have to make sure the total number of moles for the gas is constant. No matter using Charles's law, Boyle's law, or combined gas law, the amount of gas must be constant. However, if you want to include the mole of the gas, you have to use this gas law called the ideal gas law. Okay, called the ideal gas law. The ideal gas law includes all 4 variables we have talked about: PV, a mole, and temperature. And the mathematical equation is here. PV equals to nRT. P, pressure. V, volume. N, the mole, the amount. T, temperature. In order to make this valid, you have to multiply at R with N and T. This R is called the gas constant. Okay, gas constant. If the pressure you use ATM, V you use liter as a unit, N of course mole, and T Kelvin. If you use these 4 sets of units, the gas constant equal to 0.0821. Constant means this number doesn't change as long as the units are set. ATM for pressure, volume is using liter, mole, and Kelvin. If that's the case, R will always be 0.0821. That's called the gas constant. Okay, R is a known number, the constant. So if R is the constant, that means you know that number. So you basically, this PV equals to nRT, you only have 4 variables because we know what R is. That means if you know any 3, you can calculate the other one because you have 4 variables, PV and T. If you know any 3, you can calculate the other. This is the rearranged version of PV and RT. If you divide V on both sides, you get P equals to nRT divided by V. If you divide RT on both sides, you get N equals to PV over RT. If you divide P on both sides, you get nRT divided by P equals to V. If you divide NR on both sides, you get T equals to PV over NR. See that? Any 3 variables, if you know them, and again, we know the R 0.0821, we can calculate the missing one. Okay, here's one quick practice. Again, I didn't even do the practice. I just listed all the things you need to know and help you can work on the practice. Okay, an automobile tire at 23 degrees Celsius. And the volume will be 25 liter. And it is filled with air for a pressure of 2.18 atm. So see, the tire, you know 3 things: the temperature, the volume, the pressure. They ask you, hey, can you tell us the mole, the amount of the air in the tire? So all you need is list everything you know. You know P, 2.18 atm. You know V, 25 liter. You know R, 0.0821. You know T, 23 degrees Celsius. Again, add 273 to convert the Celsius into Kelvin, 296 Kelvin. So you know all 3. You need to solve N. PV and RT. If you want to know N, you need to divide RT on both sides. So N equals to PV over RT. All you need is plug in the numbers. P times V divided by R and T. Put a parenthesis of R and T when you do the math in the calculator. And then the answer will be moles because you solved the number of particles. Again, complete the exercise. I think you have the key in the note area. Okay, another exercise. I want you to do it. I have some hint for you. I will briefly go over this, but I want you to do it. I'll point out everything you need to know. Okay, here is a tank. It tells you the volume of the tank. It tells you the temperature of the tank. Like in Celsius, you need to convert it to Kelvin. And also tells you the grams of helium in the tank. Okay, we know, not grams, kilograms, right? Remember, we said PV and RT, you need pressure, you need, they ask you what the pressure. So here, this is what is the pressure is. Just divide V on both sides. So I get nRT over V. That's the pressure. They ask what's the pressure. So in order to know the pressure, I need to know what? I need to know N, R, T, and V. R we know. T, 25 degrees Celsius. You need to convert to Kelvin. V, 304.0 liter. Got it. The only thing we don't know is N, right? Mole. But we're not given mole. We're given the kilograms of helium. So the first thing, in order to solve this question, you have to convert what? Kilograms to mole. In order to convert kilograms to mole, you have to convert kilograms to grams first. K stands for what? 1,000, remember. the prefix. And then grams can be converted to what? To mole. Remember, helium, molar mass is what? Is 4. Okay, molar mass is 4. Okay, from the atomic mass, 4 grams per mole. So the molar mass of helium will relate grams and mole. So the only tricky part here is you need to convert kilograms to mole. Then you know mole, you know T, you know V, you know R. You can solve pressure. Okay, again, please practice. Okay, practice. And the last law of gas law we're going to study today is relating. Okay, sorry. Okay, see. Okay, the last law we're going to study here is called Dalton's law of partial pressure. Okay, this is a relatively simple law. It doesn't relate to a lot of variables. It's actually talking about the pressure. Okay, this law applies to a mixture of gases. Okay, mixture of gases. If we have a mixture of gas, okay, mixture means they have multiple components in the gas, in the chamber. Those gases have something that's in common, means the same. For example, if you have a multiple mixture of gas, then in the mixture, all the gases should have the same volume because they fill in the same container. And also because they're in the same container, all the gases should have the same temperature. These two variables, they're the same, these gases. But what's different is these gases will have different pressure. Because different gas particles collide the inside wall of the container differently. Some collide stronger, some collide weaker. So different gases in the mixture have different pressure. Okay, have different pressure. But now if you place these gases into a mixture, the total pressure of the mixture gas will equal to the pressure of each individual gases sum up together, or the sum of the individual gases pressure. And each individual gas pressure in the mixture, we call that the partial pressure. Okay, the partial pressure. So the total pressure of the mixture will equal to what? To the partial pressure add together. Because again, the total pressure is the total collision of all the particles. Each particle collide differently. So if you want to know the total collision, you add them all together. So P total equals to the pressure of gas 1, pressure of gas 2, partial pressure of gas 3, add them together. You get the total pressure. That's called Dalton's law of partial pressures. Okay, as demonstrated in this picture, you can see that if I have 3 gases, A gas, B gas, C gas, each one has their own pressure. If we add them all together in the mixture, then the total pressure will equal to their pressures adding together. PA plus PB plus PC. Okay, very straightforward. You have 3 components, you add all 3 pressures. Okay, very quickly, this is the quick check about Dalton's law of partial pressure. It asks you a mixture of gas containing oxygen, helium, nitrogen. Total is 780 millimeter mercury. They ask you, what is the partial pressure of oxygen if the partial pressure of helium and mercury is 86 and 124? So here we know the total, and we know the partial pressure of nitrogen and helium. Okay, nitrogen, helium, sorry, have helium. Nitrogen is 124, helium is 86 millimeter mercury. So the helium, the partial pressure of oxygen, basically all you need is to subtract the partial pressure of the helium and nitrogen from the total, because remember, O at 3 equal to total. If you want to know one of them, you subtract the other 2 from the total. So basically you're subtracting 124 and 86 from 780. Okay, you're getting Let me see, you're getting 694, 570. Okay, 570. Okay, 780 minus 86 minus 124, which is 570. So that's the partial pressure of oxygen. Okay, partial pressure of oxygen. Another exercise, I have the key solution. Okay, solution in the note area. This exercise is very interesting. It actually has two solutions. One solution is actually very complicated. Another solution is very simple, but you need to apply the concept of Dalton's law of partial pressure. It is a device like this with two chambers. They ask you, once you open the valve at the center, these two chambers get mixed together, what is the total pressure? Okay, total pressure. So you need to calculate, you need to assume these two parts of the chamber, of the chamber before open up, they are individual gases, even though they're both helium, but you can assume they're different gases. So you need to calculate the pressure after you open up for each one, then add them together. That's the simple method. Because Dalton's law of partial pressure indicates what? Total pressure equals to the pressure of each individual one. So you calculate the one on the left after open up, what's the pressure afterwards? You calculate after open up, what's the pressure of the green gas afterwards? Then you add them together, you get the total pressure. Even though they're both helium. In order to calculate it before and after, you're using Boyle's law actually, because the temperature remains the same. Nothing is heating that chamber or this tube. So you're simply using Boyle's law. Okay, think about it. Okay, I have the key solutions in the note area. It actually has both solutions there. I mean, you can use either one, but the simpler one is simply use Boyle's law and Dalton's law of partial pressure. Okay, it should be easy to understand if you see the key. Again, if you have any questions, feel free to email me or ask on Blackboard. Okay, hope you practice a lot. Again, it involves a lot of mathematical rearrangement of this. Okay, like an algebra rearrangement. Okay, something you may be not familiar with. That's why we have a web assignment. Also, spend some time on that too. Okay, so I'll pause and stop here. And in our second part of this chapter 7, we're going to talk about the change of state, and then we're going to focus a little bit something on evaporation. Right? That is all for first part of chapter 7. Bye now.